second part of homework 3, part B. So parts 3 and 4, or B3 and B4. And first part is at using the equation we just got at a steady state, meaning our left side of the equation will be equal to 0. And then we will also have a constant velocity and potential energy. And using that with a 900,000 Pascal drop, we're going to be determining how much the temperature of the liquid water would change. So we'll do our equation. So we have our dmn, and we have our h, which will be important, and then our velocity will be 0, and our potential energy will be 0 again. So, and then we have our minus dm out, which will be the same thing, h, 0 and 0. And then in this situation, our q and non-flow work will also be 0, meaning that our h in will be equal to our h out. So knowing this, we can transform our h back into its parts. So our P in over density in plus our internal energy in is equal to our P out over our density out plus our internal energy out. So in this situation, it's water, and the density will be the same. So we can combine these terms here. So P in minus P out over our density is equal to U internal energy out minus internal energy in. So we know that there will be a drop of 900,000. So we have our P in minus P in minus 900,000 over our density, which for water would be 1,000 kilograms per meter cubed, and then our internal energy out minus our internal energy in, which will be represented by CV times T out minus T in, which in our situation, we'll just call this delta T, or what we're solving for, CV. So this will be 900,000 over 1,000 is equal to CV delta T. For water, the CV is 4,186 per kilogram. So using this, we get 900 divided by 4,186 is equal to our change in temperature, and this would be in kelvins. So the change is about 0.21 degrees. Yep. Next, we're going to use the other equation we got, and it's important to note that our density is equal to PM over RT, and this M is going to be the molar average in kilogram per meter cubed for air, which is what we're going to be using. That is 0.029. So from what we just got, the right side of the equation, which would have been our frictional heating plus our non-flow work over dm, is going to be equal to 0. And that means we will have our trying to remember which comes first. So our P2 minus our P1 over the density, which in this case is PM over RT. So we'll replace that now. PM over RT plus V2 squared minus V1 squared over 2. That will be equal to 0. So we know that our M is 0.029 and our atmospheric pressure is 101.325 times 0.029 over R times T for air, 298. And this simplifies to be about 1.186. And our change is going to be 10,000. So on top, we'll get our equation back equal. So 10,000 over 1.186 plus V2. Oh, this is going to be negative because it is a drop. So our P1 is 10,000 and our P2 would be 0. So that would be a negative 10,000 for the drop. V2 squared plus V1 squared over 2. And we are going to let our initial velocity be 0, meaning this is just V2 squared over 2. This is still equal to 0. And we'll move this on to the other side. So we will get V2 squared is equal to 10,000 times 2 over 1.186. We will take the square root of both sides. And this will end us with a final velocity of around 129.8 meters per second. Okay, this is going to be homework 3, part B. In this, we are going to be writing out the equation for flow work, as well as I'm going to also be doing part 2, which is from that equation of flow work, kind of transforming it into a Bernoulli's equation, in which, what am I even trying to say, my brother? Come on. Okay. This is going to be homework 3, part B, parts 1 and 2. So firstly, we're going to be writing the equation for flow work. And from this equation, we'll be kind of transforming it into somewhat a form of the Bernoulli's equation, which will be useful for calculating other things. So, to start off, we're going to have our differential change, and our flow work will be dm times u plus v squared over 2 plus gz, which will be equal to our change times our u plus v squared over 2 plus gz, and this will be coming into our system, and then we will be subtracting our differential amount, mass times u plus v squared over 2 plus gz, going out of our system. And then we will have our flow work coming in, so that will be our dw in plus my minus our dW out plus our dQ and also plus our non-flow work. For our flow work, it's important to know it can be represented in density or specific volume to be more accurate, I suppose. But that will end up giving us our P in over our density in times dm in, and then also minus P out, the pressure at the outlet, divided by the density at the outlet, times difference amount of mass at the outlet. And since this has been transformed, we can plug this into a spot up here in this equation. So we will end up with dm times P in over density at inlet plus U plus V squared over 2 plus GZ and minus dm P out, density out, plus U plus V squared over 2 plus GZ out. And this P over density plus U can be represented by H, enthalpy. So we'll rewrite this one more time as our differential amount of work, U plus V squared over 2 plus GZ will be equal to dm in H plus V squared over 2 plus GZ minus dm out H plus V squared over 2 plus GZ. And move this real quick. And then plus our dq and our non-flow work. All right. And that would be the first part. And for the second part, it is important to note that at the steady state, this is equal to 0, so equals 0 at steady state. So we'll be moving on part B now. So we will let these two also be equal to 0 in this case. So that will end us up with something like 0 equals, and then we'll separate our H back into its two components once more. And in this situation, our densities will be the same at the inlet and the outlet. So we'll have P in minus P out over the density plus our V1 squared minus V2 squared over 2 plus G times Z1 plus minus Z2 and then we will have plus our u1 minus u2, or these aren't 0 just yet, but plus our dq, plus our dw, our work, non-flow work. And if we throw all these onto the other side, we will get our P out minus P in over the density plus V2 squared minus V1 squared over 2 plus G times Z2 squared minus Z1, or not squared, equals to U1 minus U2 plus DQ plus our work, that's non-flow. And one thing that we left out was this dm, and because it's at the steady state, what a snag, we will have our dm in will be equal to our dm out, which we can just represent as dm. And that term would apply for all 4 of these. So we will divide all this by dm, meaning we end up with here, dm down here, and dm down here. And this is what is referred to as our frictional heating. And if we were to let this side of our equation be equal to 0, it would be in a form of the Bernoulli's equation, in which we can use to later solve for things that may be missing. V2 minus V1 over 2 squared plus G times Z2 minus Z1. All right.